Okay, shall we start? Let me recap some of the things that we have done last lecture. Basically, we talk about two, powerful ways of counting. Why are we concerned with counting? Because in a lot of probability problems, the outcomes are what we call equally likely, meaning that the outcome of a random experiment, there is no favoritism among which possible outcome. For example, you toss a coin, then it's either head or tail. There is no particular preference for tail versus head. Or when you roll a fair die, there is no particular preference for a particular number. And probability comes especially at the very beginning, are motivated by gambling. In total, in Singapore, I think you out of 49 numbers labeled 1 up to 49, and then 6 numbers are being chosen, and so you will win the first prize, and so on. And again, there is no preference for whatever number that would come out, so each number will be equally likely to come out. So in a lot of these kind of situations, we wanted to compute this kind of probability, and later on we will develop the probability, which is obvious. It is the ratio of two numbers. The denominator is the number of outcomes that are prescribed by the event of your interest, and so you have to count that. Very often that can be difficult. We will see some such examples. And then the denominator is another counting, the count how many possible outcomes from a random experiment. And usually this can be easy. And then, so the two tools of counting is one what we call permutations, where the order is important, or the multiplication principle. So the idea of the multiplication principle is that the whole experiment is subdivided into different steps. And each step, you have a number of possible ways of doing it, so n1 ways. And then out of this, whatever particular method that you use in your step 1, then from this you will proceed to step 2. And then step 2, there are n2 choices, and so on and so forth. So you can see like a tree branching out, all right? And so the multiplication is just after R steps, after R levels of your tree, how many leaves are there. So basically we are counting this. And then another principle is what we call the addition principle. Now you are not doing things in sequence, but you have a lot of baskets, and each basket you have a few number of choice, n1, and then basket 2 you have n2 choices, and so on. And your idea of doing it is that you just pick one of the basket and one of the choice. That's it all. So that is versus the multiplication principle that you are doing it and in a way in a series of steps. So very often the problem itself should have quite a clear indication whether it is or and, but sometimes people may not put it in a very precise language, especially you are not in a science class. So I think you might want to clarify with the person who posed the problem to you. So out of the multiplication principle, we derive the factorial and also the permutation. Permutation is you pick a number of objects from a set of n, and then you notice the order. Very often the order is important in some sense. For example, the first guy you pick wins the first prize. The second guy is the second prize. So the order of being chosen is important in this respect. So we are talking about with ordering. And there are all other occasions that the ordering is not important. I mean, how many people you choose, say, from this class and go for a field trip. So it doesn't really matter you are chosen the first or chosen second, and so on and so forth. So in that respect, the ordering is not important, but the composition is all we care about. And so we are interested in counting how many such compositions. And so we are doing combinations. And permutation is a special way of doing the permutations, I mean the entire permutations, which we have already mentioned. Originally, I planned to skip the examples, but I think some of you give me the feedback that very often in a lot of classes, we go through some easy example at the beginning, and then we skip the more less trivial examples later on. So I think this is a good point, and so we'll try to cover some of this. Okay. Now this example is pretty easy. But later on, this has something to do with what we call hypergeometric distributions. Let me say it here, the motivation behind. Very often we are interested in estimating, say, the number of fish in a lake, let's say. So of course, to estimate this, it can be very difficult. One brute force way is, I mean, take out all the water from the lake and then you count them, but then that would defeat the purpose. One way is what we call capture-recapture, which is often used. So what you do is you capture some fish from the lake in your first try, and then tag the fish, and then put the fish back into the lake, and wait for a while. I mean, so that basically the idea is that the fish, the tagged, and those that are not tagged, which is uncaught in the first try, they mix well. And then you go for the second catch. Now, in your second catch, some fish are tagged. That has been caught before. That is called recapture. And some of the fish are not captured. By how many fish that you have captured earlier, in proportion to your how many fish that you have captured in your second catch, there is some way to do that, and that is a hypergeometric distribution. Now, this is something similar. The bad apple, you can think of it as has been captured before, and then there are a total of 30 apples, and then 25 here is the good apple, but you can think of it as the apples that you have not caught before. All right? So here, basically, you do it this way. So you think of this coming from two batch. So this is the bad apple, and this is the good. And then you have 25 here, and then 5. And you just want to pick 5 in your part A. So regardless of the apple, so you have 30 of them. And let me peep at the answer first. All right. Now, of course, the way you think of it is the apples are distinguishable. Okay, so that is. Oh, thank you. Is it all right? Okay. Here, you are thinking of all the apples. You can tell them apart. Now, of course, I mean, this is a bit stretch for apples. All right. So, but anyway, you have 30 apples from which you choose 5. So this is according to our formula. So we have this. We can work out this number in a moment, but it is quite a big number, 142,506 way of doing this. And then for part B, you want 4 good apples and then 1 bad one. So, so you have to choose 4. So you think of it as this experiment comes in 2 steps. Choose a good apple first, and there are 25 times choose 4 ways of doing it. And then your second method, your second step in your experiment, you choose a bad apple, from which you have 5 choose 1. And so you can just work out the number. And so this is 63,250. Okay. And now part C is you want at least 2 bad apples. So one way is that okay. Maybe it's easier to look at the opposite. 2 bad apples means 2 bad apples, 3 bad apples, 4 bad apples, and 5 bad apples. So you have to calculate some of this. And now here you have to do addition because of either you have 2 bad apples in your choice or 3 and so on. So you will use addition here. But the opposite might be easier, less than 2 bad apples. And so that would be equal to, consists of no bad apple, well, I think red is a little bit, doesn't show up that well. And then, or 1 bad apple. It's bad handwriting for sure. Okay, so this is easier because, I mean, you have less case to calculate. So if you are looking for no bad apple, so that means all of them has to be chosen from this basket, 25. And of course, you just don't do anything. Or you can think of it as 5 choose 0, which is one way. And then here, 1 bad apple, which we have already done here. Okay. And so you can see in your lecture notes, you see we take away 5 good apples and take away 4 good, 1 bad apples. And so that's it. All right. So let's do some of the calculations in the software. Of course, you can do so using your calculator. So the command for combinatoric is for combination is choose. So I think this is easier to remember. And then so out of 30 apples that you just pick 5, so you get this answer. And then another one, part B, is you choose you choose 4 apples, 4 good ones. So that must be from 25. And then you choose the 1 bad apple from the 5 bad ones. So this is it. All right, and so on and so forth. So so it is quite handy. You don't need to bring your calculator along. I mean, you just do everything on your computer. Okay, so this all about bad apples. Okay, a committee of 3 is to be formed from a group of 20 people. And then how many possible committees can be formed? So this is, again, similar questions. I have 20 people, and then I wanted to choose 3. Okay, so I have 1,140 possible such committees. All right. Now, suppose that I have 2 guys. They are enemies. They can't serve together in the same committee. I mean, this kind of things really happen. All right. How many possible committees can be formed with restriction that these 2 guys don't serve together? Now, there are 2 ways to attack the problem. One way is head-on. So you have to break the committees into 3 categories. Category 1 is that both Peter and Paul are not in. So that means you have 18 people, and out of which you choose 3. So this is one class of committees in which Peter and Paul don't even serve in the committee. Another one would be Peter is in, but Paul is out. All right? And then the third category is Paul is in, but Peter is out. So you can do so. So the first category, you choose 18 out of 3, and then plus you choose 18, you choose 2. All right? Now, of course, Category 2 and Category 3 that I just mentioned about Paul and Peter, but they are symmetric, so you can multiply by 2 because the Category 2 and Category 3 give you the same numbers. So that would be one way to do so. I think in the lecture notes, they do it in the opposite because, in fact, you don't gain exceedingly large, you don't gain exceedingly advantage because, it's quite easy here. One way to go about it is that I have no restriction on my committees. So the committees there are 2 types. One type is both Peter and in, and that is the type we want to exclude, right? And so this is what we want to do. So we have 20 of them, and we have no restrictions. So this is counting all possible committees. But all these committees can be classified into 2. One is the impossible committees, those that Peter and Paul are chosen. So when you insist Peter and Paul are chosen, that means the other 18 guys, I can choose only 1. And of course, the 2 here refers to Peter and Paul, and I have to choose 2. All right? So I get back the same answer. All right? So that is how your lecture notes proceeds. Is that all right? Now I'm going a little bit at this kind of pace because I don't know whether I will bore you to sleep or you want me to slow down a bit. So just make some noise. Not snoring noise, all right? So, but if you really think that I'm just, wasting your time, give me some hint so that I can move a little bit faster. So this is basically here. How many ways can 4 men and 3 women sit in a row if no 2 women are allowed to sit together? So this is one way to go, is that I put the men first, okay, M1, M2, M3, M4, and then there are 5 spaces left, all right? And out of these 5 spaces, I have to choose 3 spaces to put the 3 women. And then I will ensure that the women will not sit next to each other. So that's the whole point here, all right? So depending on the choices of the 3 chosen here, for some of the men will definitely sit next to each other. Okay, so the first thing is there are 3 factorial ways to arrange the woman. And then 4 factorial way accounts for the ordering of the man. All right. So this is how to sit the man. And then I leave out 5 spaces, and out of which I have to choose 3 spaces to sit the 3 women. All right. And then, of course, once they are seated, the women, they can rearrange themselves to give different kind of arrangements. So this is a 3 factorial way of doing it. Is that all right? So I guess the best thing to do is you sort of here. I mean, of course, for doing exercise, you can just write down the answer, and then maybe below here you point out why you get the 4 factorial here, and then why you get this and why you get this. So I think that is pretty clear. And in exam situations, I think that would also, at least for me, is pretty clear that you know what you are doing. Okay. So again, this is 4 black marbles, 3 white marbles, so no 2 white marbles are consecutive. This is the same questions, right? You just do a translations. Black marbles corresponds to man, and then white marbles to woman. So I don't know why this example is there, but just to illustrate that black marble is just a label. You can think of it as man, white marbles as woman. All right. So so what you are solving is not a particular problem, but sometimes a little bit more general than that. So let me just skip through it. All right. One of the things is that if we are out to calculate probability, there are certain situations that you have to define your approach first. Now, by defining the approach, basically, in our jargon, is modeling what kind of assumptions that you are making underlying the experiment that you're looking at. Now, for example, I roll a die, and then you say the probability of getting 1 is 1/6, and 2 is 1/6, and so on. You are basically assuming the die is fair, all right, not loaded. Now, if you notice in some movies or in casinos, the die, let's say, very often the die is red. I don't know why, and then they have a filling. Usually it's white to fill up the number. Now, I think the idea is to make sure the die has an even distribution of material, so that it would be fair. The argument can go like this. If you look at the 6, they carve out 6 circles, right? Now, if you don't fill it in, that part would be lighter than the other part. So some people, you can take advantage of this, all right? So I will tell you more of these things as we go on. So this is called equally likely. So we assume each of the outcomes have no preference against one another. So that is why you actually don't distinguish them. So as a result, you are doing the equally likely outcomes. And then another one is what we call frequency interpretations. You do not quite know the probability, or you are thinking of, if I repeat the experiment over and over again, what is the percentage that I will see the outcome that you are interested. So again, say for example, you do not know whether it's 1/6. One way is that you roll your die many times, and then see whether you see about 1/6% of the time, 1/6 proportion of the time that you will get 1, right, and so on and so forth. Similarly, people are flipping their coin and then look at the percentage of heads that they have. We are aware of someone did it because he was a prisoner of war. Later on, we will talk about him. He actually, in his jail, when he was in prison, he really flipped the coin 10,000 times and take records of each flip, whether he get heads or tails. So he, do a frequency plot. We will show it when it's the right place to do so. And then there is something like a personal probability. Probability that based on your experience or just top of your head. Now, these things you have to watch out because the probability can be just a very rough number, depending on the person too. For example, if you, I don't watch the EPL because it's usually very late in the night, but I do look at the result. Usually when the match is going on, before the match, if you, they will tell you, say, the one that I remember vividly is Newcastle versus Arsenal just recently. And then at the beginning is something like 17% Newcastle will win, and then 11% that they will draw, and then the remaining probability is something like Arsenal will win. When Arsenal score, then you will see they actually plot the percentages. Then suddenly the red line, which represents the percentage that Arsenal will win, shoot up. All right. So I have a former student. I hope he has changed his job. His first job, I think he was working for a company, which he didn't tell me the name. The company take on online bet of the EPL, and so and they allow you to bet even the match is going on. So the company keep track of how many corner kicks, how many shots, and how many are on target, and so on and so forth. Then they keep on actually updating the probability. Now, of course, they probably not entirely using personal, but probably a hybrid, a mix of experience versus some frequency interpretations. So, so my point is, the personal probability can be very much off. All right, but but this is not our point here. Whatever approach that you use, mathematics do not really care objectivity. You might be surprised that we are not very concerned about whether something is objective or whether something is subjective. If you think about it, what is objective, right? Anyway, if you push it further. So what we care about is the consistency of the assignment. This is actually we will formulate in terms of a rule later on. And there are some situations in which you can actually calculate the probability using an equally likely outcomes. We will do it in the birthday problem, which involves a little bit intricate calculations. But we can also do frequency interpretation because to mimic the assumption, what I can do is I create a rather large hat, the magician hat, and then I have 365 tickets and put it into the hat. And so I pick one, which corresponds to the birthday of the first person, and then I put it back into the hat, and then I randomly pick another one. So what I'm describing is that you can ask a computer to do so. And so we can repeat it many, many times. Suppose I'm interested in the probability of having 23 people having a common birthday. I can simulate drawing the tickets, 23 tickets with replacement. Then I do it one time. I observe whether I have someone that share the birthday, meaning that do I have a ticket that has been drawn more than once? So I repeat it 10,000 times. All right. Okay. Of course, you won't do that. It's really time consuming. But the computer can do it within a very short while. Okay. The equally likely outcomes, if there are n equally likely possibilities. So this is actually our big assumptions. All right. Equally likely possibilities. Usually we do not say it this way. We say the coin is fair, the die is fair. and blah, 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 all right? So we do not really spell it out in such technicality in this way, but this is the actual assumption behind. So the probability of an event A with S outcome, meaning that the set A has S elements, then the probability is equal to S over N. So the combinatoric will come in to know what is S and what is N, okay, in a large number of problems. And this falls into the equally likely regime, all right? Now, the nice things about this kind of approach, equally likely outcomes, we don't even have to perform the experiment because everything can be done in conceptual considerations. All right. So, for example, I don't really need to seek out even a con and then to show that it is probability half because my argument is actually experiment free. I mean, basically everything is done in the head. All right. Okay. So the probability of drawing an ace from a deck of cards is 4 out of 52. So here, of course, I assume the deck of cards is well shuffled, and so each of the cards is equally likely to be chosen. Now, of course, this is the basic assumption, but if you pull out a new deck of cards and then you don't shuffle it, of course, you know where the A's are. All right, so then the probability will be different. Okay, what if you can't break it down into equally likely outcomes, say the probability of rain tomorrow? This is now something, if you assume whether it rains tomorrow and it does not rain tomorrow as equally likely, either you will find that this is a way of modeling. Now, people will challenge your model, but then, of course, if you insist on it, I mean, nothing wrong about your model. Except that your model is not realistic, all right? So, statisticians, I think he put it very nicely. George Box, he passed away, and he was a chemist by training, but turned into statisticians during the Second World War. He mentioned that all models are wrong. Some are more useful, all right? So basically, modeling is an idealization of something that is happening. And some modeling is more realistic, and so as a result, it is useful to do predictions or to do calculations. But then some other kinds of model are really off, all right? And so they are not useful. The frequency approach, the probability of an event is the proportion of times of the event will occur in a long run of repeated experiments. So repeated here, I wanted to emphasize, is that it is an independent fashion and under the same condition. Okay. So, and usually we resort to the computer to do it because the computer is capable, or machine is capable of independence without having the memory affecting it. One of the very classical example, you can search for it online, is that I can do fraud detection. Suppose I assign one of you to flip a coin 100 times, and then you really recall it whether you get head or tail. So you have 100 outcomes of your 100 flips, so like head and tail. And then another one of you, you do not flip your coin, but then top of your head you write down H and T and so on and so forth. And if you don't tell me who actually did the flipping, and then who actually make it up, there is a lot of statistical situations that I can determine whether you actually fake it or you are actually tossing the coin. The reason is this. For people who are faking the head or tail, you actually remember what you have written down earlier. And sometimes you will tend to switch. After, say, for example, 5 hats, then you start to, I should write T. It's because you remember you have written 5 hats consecutively. So there is a switch. But the machine, if you really flip the coin won't remember. Earlier, I landed hat 5 times. Maybe this time I land tails, right? So because this is an inanimate object, it does not quite remember. So as a result, people who are faking this kind of flipping by writing it down, people know that there is a more switch than actually is, okay, when you flip it. So this is one of the clues. And then there is another clue that when you really flip the coin, there are occasions that you have consecutive happenings of heads or consecutive happenings of tail. But this is called maximum run length, okay? And if you are faking it, you usually chicken out. After you have 3 or 4 heads, then you say, oh, I better change it to T. Now, so these two things, there is a more often switch when you are doing it because simply you remember what you have written. And then you also see what you have written earlier. Then you tend not to have a stretch, all right? So these two combined together, of course, defining the threshold will be based on some probability calculations. So basically, people formulated 2 thresholds, and what is the maximum stretch, and then how many times you switch from head to tail or tail to head. They have a good clue that whether it is a real flipping the coin 100 times or you are faking it. Now, of course, if you flip, sometime you make it up. That would be difficult, all right? Okay, so this is the independent, and also under the same condition. So this is what we call, the jargon will be IID, independent and identically distributed, okay? So this will be very often our assumption. Probability of a jet from New York to Boston arriving on time is 78%. What we mean that flights like this over the long run will arrive on time 78% of time. Now, the accuracy of this would not be exactly 78% for the coming flights from New York to Boston, but it is a good gauge, 78% plus or minus something, all right? And later on, we'll talk about plus or minus what, all right? So you have some allowance. Now, this is what we call frequency approach based on historical data. So we look at the historical data. Now, there is always a balance between how far back you look at. If you look far back, so of course you have more data, so you have a better estimation. But then, of course, if you look too far back in the history, then conditions might have changed. It would be so whether the situations are identical would be difficult to justify. So this is the usual situations of estimating the probability using historical data. Suppose you estimate the temperature, and if you believe global warming is on the rise, then if you look too far back, say 100 years, do the data of the past year, the same situations as the data in 100 years ago. So whether you should lump them together and do the estimate. So this requires some thinking. But what if the event is not repeatable, like the probability of you getting promoted this year? So we define the personal probability of an event to the degree to which a given individual believes the event will happen. So sometimes the term subjective probability is used because the degree of belief may be different for each individual. And that is why in some judicial system, we have a jury system, and so each one of them, each member of the jury will have a different assignment of the probability, whether the suspect is guilty or not guilty. Okay. Okay. I think there is a 95% that she will say yes if I propose. Well, depending on what you propose. All right. Sometimes it can be thought of as willingness to place a bet. Now, one of the things is that people suggest how to have a sharper personal assignment of probability. One way is this is the probability of certain things. So let's say whether it will rain tomorrow. Now, if there is no consequence, your guess might be, quite arbitrary. But if you are thinking of a system of bet, say one system is you have one white ball and then 99 black ball, and you give yourself a prize. If you pick up the white ball with probability, you will win, or you can choose to guess whether it will rain, you will win. Now, so that would force you to look at the probability that you are assigning to probability of rain a little bit more meticulous, okay? Basically help you to focus in your estimation. Now, if you think that the probability of rain is a better bet than picking a white ball out of 99 black ball, so at least you know the probability of rain is at least, you ask yourself, is likely to be bigger than 1%. Then you ask yourself, if I'm offered another system, there are 10 white balls and then 90 black balls. Will you play this game or do a prediction of whether it will rain? So basically, this kind of intellectual exercise is to help you to sort of zoom in a little bit further for your estimation rather than just 5%. So it just forces you a little bit more. Okay, maybe I think I will have a break here for 5 minutes. The ideas of, as I mentioned, in mathematics, we are not out for objectivity. What is truth anyway, right? That is difficult. But in mathematics, we actually set a rule. And within the rule, you play the game. So that is the deductive part of mathematics. It's just like if you're willing to play bridge. There are a set of rules that you have to obey. And if you don't like certain rule in bridge game, then you play other game, right? So if you decide to play bridge, that is the set of rules you have to obey. So this is the situations here. In probability, we will have 3 rules. One of the big rules is the consistency. For example, I say the probability that you lose is 70%. Then I can't say, later on I'll say the probability that you lose will be 70%. So that would contradict my earlier statement. So this is the consistency that we want to impose on. All right, so maybe we'll have a 5 minutes break. Please come back at, say, 10:50. Okay. Yeah, right, okay. Oh, you're doing. Okay, so you are registered at L2. Are you registered in one of the... I'm not registered, I'm feeling at home. Oh, okay. But if you bid successfully... Yeah, that means... Okay, so can I have your name, your email address, and also your matriculation number? Because I don't know what they ask. That's a V, right? You. All right, and how about your email address? Can you just yeah. A012543. All right, thank you. Yep, thank you. So how does it work? Like I'll get a link to the I will add you into the guest, so I don't know. I think then you can access the phone. When I upload something, then I think those who are in my guest list as well as my students will automatically receive the email notification. And then you just click the link and then you don't even have to go to Luminous. Then you get it. Oh, yeah, I think. Okay. Yeah. Thanks for the feedback from one of you. I was translating the black marbles as men, and then white marbles as women. As it turns out, here the calculations assume the marbles are not distinguishable, whereas the man and the woman are. So the calculation is a little bit different. Thank you for the feedback. And in fact, if you have any of this, let's get it done, and then let me correct what I mentioned. Let's go to the different approaches. So this is the main thing. So the probability of an event is simply the number of events in number of outcomes in A, in the event A, over the total. Yes.
Why are men and women distinguishable?
I don't know. You can tell this is Peter, this is Paul, and so on and so forth.
But in the examples that we have had,
the apples, huh?
say 4 people, 5 people sitting in the chairs and stuff, right?
Yes.
You don't say Peter, John, and Mark.
But here, over there, we do assume the people are distinguishable. If they are not distinguishable, then there is only one way of sitting them, right? Now, of course, I think it is, I can defend man and woman, you can tell them apart. Maybe you can't tell the cats. I mean, this is Peter, this is Paul, apart. I mean, especially if they look alike. But of course, I can't defend about the apples. So just now we have 25 good apples and all this. So, I think the whole point is some of these assumptions you can challenge it. All right. Now I have to say, I'm in examinations or in quizzes or homework, you are more than welcome to clarify them. All right. But then when you're working, depending on your colleagues, whether, I mean, depend on the personality. I mean, some people think that you are trying to be too smart. I mean, so you have to be street smart. Try not look smart, but be really smart. All right. So, all right. So here, so this is the counting things. So we will have a number of examples. So this is in a lot of card games. Ace is something that you are interested. So that is why we are interested in this. We talk about frequency approach, and one way is the most common ways nowadays is you do simulations. This is very frequently done. If you are able to prescribe the entire modeling, what is going on, and so on and so forth, then you put it into the computer and then ask the computer to do it. And then you can ask your computer to repeat doing it over and over again. But each time when the computer is doing the repetition, you observed whether a certain event that you are interested has occurred or not occurred. Then you basically do a lot of counting. So the first time when your computer run it, there is no occurrence of the event of your interest. So you put a 0 in the first try. Then you, in your second try in your computer, and if it fails again, so you have a 0. And then the third time is you have it, then you put a 1. So you now, if you simulate it, say 10,000 repetitions, so you will have 10,000 numbers of zeros and 1. So basically, then you count how many ones are there in your total 10,000 time runs. So this is possible. But of course, talking about the flight arrival on time or not, from New York to Boston, 78% you can't quite use a computer to do it. Then of course you have to look at historical data. Now, I mentioned about historical data that you have to watch out, because nowadays I think a lot of airlines are want to meet the target of online. So actually they allow pretty good allowance. For example, in the past when I went to Hong Kong, the famous Hong Kong, usually they would say the expected arrival time. So usually they give about 3.5 hours or 3 hours and 45 minutes. But now if you book a flight from SIA or some other airline, they allow 4 hours. So actually, given them, actually the actual flight is probably 3 hours and 30 minutes. Then they give themselves a better allowance. So as a result, their on-time target is easier met. So now if you are looking at the percentage just now, if you look far back, there might have a change of policy in what is the expected arrival time. So if you look far back, the arrival percentage on time is not as good as nowadays, but because they have changed the definition. The same for unemployment rate. Sometimes in the history, in a certain country, they might have a new definition of what is meant by unemployment. They classify those who are seeking job or those who are actively seeking job versus those that they just want to have a 1 year gap year. They distinguish these two categories. So the definition is different. Okay. So we talk about personal probability. And so this is something that we are interested is the consistency is required. Meaning that if you say probability of certain things, and then later on you say probability of the same thing, you don't want to contradict your two assessments. Okay, so there are altogether 3 rules. The first 2 are pretty, obvious. And then the third one is also very obvious. The probability denoted by P is a function on the collection of events satisfying this. So the more advanced probability course will think of probability is a set function. Set function means the domain of the function is collections of sets. And then you assign the elements, which is a set, into a number. So this is a set function. So the set function satisfies the following rule. The first one is that the probability of an event has always to be sandwiched between 0 and 1. So basically, we wanted to have a non-negative number to gauge it. And then another thing is that the probability of the entire outcomes that you can see has to be 1. You think of it as a normalization, because if someone else use a different normalization equal to 2, then the probability for one person, say 50%, if your reference point is 1, then this is really half. But if your reference point is 2, then it is actually 1/4. So setting it equal to 1 is sort of, we are using the same ruler to measure the things, all right? And because of, later on we'll see, this is the largest event possible because A has to be a subset of this sample space. So we know that a bigger event will have a bigger probability. So that would force this part to be less than or equal to 1. We can slightly improve the axiom by just requiring the probability is non-negative. We don't need the right-hand inequality here because we can do it a bit later. Now the key assumption is the following. For any sequence of mutually exclusive events, A1, A2, the mathematical notations means AI intersect AJ is empty as long as I and J are different. So if you pick any sets or any events in the sequence of events that you are considering, any pair of events will have no common outcomes. All right, so this is what it says. So if you draw in a Venn diagram, all the A1, A2, they are actually different circles on your Venn diagram. and the probability of the union of all these events is the sum of all of the individual events. Now here, why do I say this is consistency? Because you think of it as you have two ways to calculate the probability of, let me call this event B. B is the union of all the A here. All right? So there are two ways to calculate the probability because B is an event. So according to the fact that P is a function on the event, so P would say something about the probability of B. Okay, so the left-hand side is saying that I go back to this function and then find out, what is this probability. But on the other hand, I do have the probability of individual parts. So if I add them up, the two answers have to agree in that sense because they don't have common outcomes. All right, so I should have this. So this is the consistency requirement. Now, that's it. We have no other assumptions. So I think the beauty of probability, advertisement time, so is this. It is just three simple assumptions, and then everything else is deductions. All right? Okay. So I'm just putting in some remark. Axiom 1, the probability of any collections of outcome is a value lying between 0 and 1. The probability of all outcomes, Axiom 2, is equal to 1. It is a sort of normalization so that we are using the same currency. Axiom 3, for sequence of mutually exclusive events, the probability of at least one of them occurring is the sum of their respective probabilities. So the Axiom 3 is saying that you can either do the probability as a whole, the union, or you do it parts by parts and then add them up. The two answers should agree, all right? And that is part of this axiom here. Okay, the history of probability. The history of probability actually goes even way back. The Pascal is the famous Pascal for one of the computer language. I don't know whether people still use it anymore. There is a little story about Pascal. Pascal was born rather weak. So I think his father is an engineer, doesn't want Pascal to study mathematics. This is too, taxing for a child. That is the father's view. All right. And so I think basically the father hid the mathematics books from him. But then he noticed that when Pascal was, drawing things, he was actually working out the trigonometry. In his own terminology. So then the father realized Pascal has a talent for mathematics. Pascal later, when we talk about expectation, I will mention it, but I'll mention it here. Pascal, I think, believes in the existence of God. All right, so he say. It is better to believe in God than not to believe in God. Because if when you die, and if there is no God, there's nothing. But if there is a God, and then when you die and you didn't believe in Him, you are ruined. So in terms of expectation, it is better off to believe God exists. And so that is one of his arguments. Now another guy is called Fermat. His last statement is called the last theorem of Fermat last theorem, was only proved maybe within a decade or 2 decades ago by Andrew Weil in Princeton. Fermat is a judge by profession, but I think he's probably a terrible judge because he spent most of his time in mathematics. His last theorem basically saying that x to the power n plus y to the power n equal to z to the power n. Now, when n equal to 2, this is your famous Pythagoras theorem. So he says that when n is bigger than or equal to 3, this equation admits no integer solutions. Now, it has been verified by computer for a lot of n, for n when n is prime, and so on and so forth. No one is able to give, the entire proof. It's only happened quite recently. From the compared to the history, all right, it's about 400, close to 350 years, and so it was finally settled. All right, the beginning of probability start with Pascal and Fermat. They write letters. All right, so I think there are two basic problems that they discuss, and one of the problems is the following. A and B are playing a game, and they are equally good, so the probability of win is half and half. And they are agreed that whoever win 5 games will win. Okay, each one put down 16 units of currency, and so totally 32. Now, the question they wanted to ask is that somehow the game cannot continue. And when the game is stopped, A wins 3 games, B wins 2 games. The question is, how should they divide the $32 in a fair manner? All right, so that started the discussions. And I think Pascal and Fermat have 2 different solutions to it. All right, the probability has a hard time throughout the centuries to be recognized as a real branch of mathematics, unlike geometry or algebra or other things, because some of the terms or terminologies are very, not very much, it's a little bit vague, not very well defined. Kolmogorov in 1933 get it settled. He basically put the probability into the framework of real analysis. What the word is measure theory. He framed the probability in measure theory so that it would now be a respectable branch of mathematics. Okay, but probably only old people are interested in history because there are not much to look forward to. You guys have a lot of things to look for. So the properties of probability. Now, only using these 3 axioms or these 3 rules, we illustrate that we can deduce the following useful propositions. The first one, the probability of empty set is 0. I don't know whether it was written here. One way to go about it is this. Okay. I think I'm a little bit sloppy here. So axiom number 3 is what we call countable union. That is the actual formulations. To deduce it to finite union is you need a little bit of reasoning, but I'll just be sloppy here. So one of the axiom 3 is that if A and B are disjoint. Oh, thank you. If A and B are disjoint, then the probability of A union B is equal to the parts. All right? So now take A equal to empty set, B equal to empty set. So A and B are disjoint. All right? And so the probability of A union B, empty set union empty set is also empty. But according to this rule, you can do it parts by parts, and which is probability of empty set plus probability of empty set. So this number is equal to 2 times itself. So the only possibility is that the probability of empty set has to be 0. So this is a deduction from our assumptions, all right? So the empty set is 0. Okay. Okay. This is what we call finite union. All right. So I only have finite number of them, whereas the SIM3 is saying that I have a countably infinite sequence of events. So so the proposition 2 differs from the SIM3 is that proposition 2 says that our rule number 3 implies finite union is still okay. So we don't have to have it. Because now if you believe in proposition 1, one way to change this to infinite is to let an plus 1, an plus 2, and so on and so forth equal to empty set. Then you have your a1 up to an, and then you fill in the rest of the sequence by empty set. And then so this part would be the plus the probability of an plus 1 and an plus 2, those that you miss, right? And that are probability of empty set. And the probability of empty set is 0. So basically you can stop adding things up here. All right, so I'm not going to say a little bit more, but here is saying that you can take your SIM3 also applicable to finite unions of mutually exclusive events. Okay, the probability of A complement is equal to 1 minus probability of A. You can think of A complement is the opposite statement of A. Now you should think of an event as a statement describing what kind of outcomes that you want. All right, so it's a statement, and A complement is the opposite of the statement, or you guys, it's called the negation of the statement. All right, so the probability of the opposite of an event A is equal to 1 minus the probability of A. So this is easier to remember in Word, but it is fairly obvious. So one way to think of it is the following. Let me see whether we prove it. We didn't. So so one way is that you think of A and then A complement. All right. So consider. And so the first thing we notice is that they are mutually exclusive. All right. Because A and A opposite can't have a common element. So as a result, if you are looking at A union the opposite, and this is by rule number 3, will be equal to their respective, the probability of their respective part. And here I wanted to simplify this a little bit more. A or A opposite means everything, right? Okay. And now our SIM2 says that this is equal to 1. Okay, and so rearranging the terms, you will get proposition 3. So, so proposition 3 is a direct consequence of SIM2 and SIM3. Okay, since I'm using the visualizer, I may as well go to proposition 4. It is easier to remember in Word in some situations. I put it this way: bigger event, bigger probability. Okay. So the situation is the following. This is an event B. This is the event A. So the proposition 4 says that, wanted to say something like this. All right. So we conclude the probability of A is less than or equal to the probability of B. So this is what the slogan is. I mean, B is a bigger event than A, meaning that B is a superset of A, or A is a subset of B. And So probability of A, this portion has to be less than or equal to this portion. The way to go about it is this. You think of B consists of two portions. This is the donut part, and this is the whole. All right. So B is actually A union. Now there is some way to describe this annular ring. It is the A complement intersect B, right? A complement means outside A. Intersect B means it has to stay within B. So that is this portion. Okay, I need a bracket because this should. Otherwise, I have ambiguity in the notation. The first thing is this event and this event are mutually exclusive, right? Because if there is an element that belongs to both of them, this element has to belong in A, but this element has also belonged to the opposite of A. That is not possible. So since they are mutually exclusive, axiom number 3 kicks in. So I will have this. All right. So what they say is that the probability of this circle B is actually comes from the probability of the whole plus the probability of the ring. And so since this is axiom number 1, this is non-negative. So if I drop this, my right-hand side will possibly be smaller. So I have less than or equal to the probability of A. So that is the conclusion of the proposition 4. Okay. This is the inclusion-exclusion principle. This is the first one. There is a full generalizations of the inclusion-exclusion principle. And then related to this, there is this thing called Bonferroni inequalities. Now, all these are related, and there might be occasions that you will encounter this either in this module or in your subsequent study. So the trick of proving this, the first thing is that, let me give you an idea. Now, here the assumption is that I do not impose any assumptions on A and B, meaning that A and B can be mutually exclusive, can overlap. Now, if they do not overlap, that is actually our axiom number 3, all right, or our earlier proposition 2. Okay, so here the only change is that I have a more general situations without assuming that A and B are mutually exclusive. Okay, meaning that there is a part that is this. So the probability of A union B, the reasoning is this. When you add the probability of A, you have already included the part that belongs to A and B. And you also have included the part that is belonging to A and B also in this term. So you have counted the one in the middle 2 times, and you should only count it once. And so that is why you have to take away one of this. Now, the picture will illustrate this. So this is our A. This is our B. So one way to think of this is my A1. And this is my A2. And then this is my A3. So now, because of the device here, so A1 is actually equal to A intersect B complement. And my A2 is A intersect B. And then A3 is equal to B intersect A complement. So the A union B can be written as A1 union A2 union A3. And so, of course, you have probability A1 this is our probability of A intersect B. Okay, now we need to work out this part. probability of A1, you can think of it now. So let me draw this again. So this is my A1, and this is my AB, right? So this is the same. A is in itself is equal to A1 union A intercept B. So we are doing something similar. So probability of A would be probability of A1 plus probability of A intercept B. This is what I was referring. You are adding the middle part once, and you will do the same here. That is why you add this middle part 2 times, which you should only add it once. So here you replace it here. Probability of A1 is equal to probability of A minus probability of A intercept B. So you put this back here, and then you have a similar statement for A3, which you replace this by B, and then you interchange the role of A and B, basically. Then you have, so you will subtract this part once here, subtract this part once here. So the net is, you basically subtract it here once, all right? So that is the proposition 5. Why do people call this inclusion-exclusion? Is that, so this is the thinking. So you first include everybody, but you found that the middle part is being counted more than once, so you have to exclude it back. So the same thinking is this. Now you have 3 sets. So first you go around everybody, all right? And then you exclude this part, exclude the part that is common to a pair. But then you realize that you are excluding the one that belongs to 3 of them 3 times. I mean, so which you have included it 1 time, 2 times, 3 times. So when you take out the middle part, you actually take out this. There is nothing there, all right? And so you have to add it back. So that is now why the thinking here, A union B, A union C, is equal to probability of A. This is the inclusion part. But you realize that you are including too much. So you start to exclude things, exclude those that are common to a pair. But then you realize that you are now excluding too much, so you have to put back something in order to count it well. So that is why it's called inclusion-exclusion principle. For 4 events, it is almost impossible to draw it in a common way, in a general manner. But the idea is the same. If you have 4 sets, so you include every individual set, take away all the pair. But when you take away the pair, you take away all those that belong to 3 at a time. So you have to add them back. But when you add them back, you suddenly realize that you have add up those that belongs to all of them 1 extra time. So you have to subtract it back. So it is like you include everything, and then you find it's too much, you push out some, and then you find that you push out too much, you include it back. So this is the first of the inclusion-exclusion principle. Okay, so here this is what I mentioned. So this is the 1 event at a time. So you include all the 1 event, and then you exclude all the pair events, and then you have to include back 3 events at a time. So you do it 1 pair, and then triple, and then quadruple. So the quadruple you have to subtract it now. Okay. I'm not sure whether we will talk about Bonferroni inequality. Bonferroni inequality means, suppose, say, you only keep the first line, and then you decide I mean, it's maybe too much trouble to do the second line and the third line, then of course you don't expect it is equal. But Bonferroni inequality says that if you only keep the first line, it would be your upper bound of this number. So this probability would not be more than your first line. But if you decide to drop the third line only, meaning that you include the second line and the first and the second line, but you drop the third line, Bonferroni inequality says that it would be a lower bound on your probability. So if you keep the first line, you will have an upper bound, and if you keep the first two, you have a lower bound. The thing is in between. And if you keep 3 up to 3, then it will also be an upper bound. If you keep up to 4 lines, then it will be a lower bound. So it's something like alternating around your the things that you're looking for. The entire inclusion-exclusion principle saying that if you keep seesawing, then eventually you get the right one. Okay, sample spaces having equally likely outcomes. So let's see. So basically we have some of this. So there is nowadays a reverse way of asking. Suppose the possibility of all outcomes are very large and you have no clue what this n is. One way that in nowadays doing simulation is the other way around. You define a certain event and then you use simulation to estimate the probability. But you have some way to count this. You have some way to count. Okay, you have an estimation of this, and then you also have an estimation of the elements of A. So you will be able to, from the probability, you will be able to estimate back the n. All right. So because basically the probability is the ratio of two things. So you think of there are actually 3 terms. One is the probability that you are interested, and then you have the numerator and denominator, right? As long as you know 2 of them, then you'll be able to know the remaining one. So depending on the application, sometimes it's the denominator that we do not know, but we can use simulations to estimate the left-hand side. And so, and I know the numerator, so I'll be able to say something about the denominator. Or the other way around. In computer science, sometimes people are interested to see whether a certain statement has a solution. And they care about whether a solution exists or not exists. And if the entire thing is equally likely, and if they are able to show that the probability is positive for that particular statement, then that means the event A will not be empty. So that means there at least one solution. So that is quite a roundabout way of proving something that have a solution or is solvable. But that in very hard problem, people are, you just have totally no clue. And if there is some way to estimate the probability from below, and you are able to show that the lower bound is positive, then that means actually your numerator has to be positive. So that is one of the approach here. Okay, so this is actually what we are aiming at. It would consist of 2. Basically, I have 3 terms: the probability, and then the number of elements in A, the number of elements in the entire sample space. So the whole thing is you can, as long as you know 2 things by some means, then you will be able to know the others. So that is the key. But of course, from this module, our main concern is the left-hand side is not known. So it would reduce to computing the numerator and the denominator here. Okay, a pair of fair dice is tossed. what is the probability of getting a sum of 7? Okay, and so this is by enumerations. So I have 1, 6, meaning that the first die give me 1, the second one give me a 6, and I have a 2, 5. So they all add up to 7. And this is it, all right? Now, so in this kind of problem, if you resort to enumerations, in this case, of course, you can use pencil and paper. Another enumeration would be, I mean, if you have a systematic way of enumerating them, again, you can write a program to enumerate them case by case. Some of you might have heard about the 4-color problem, meaning that if I have an arbitrary map and then different countries, no neighboring countries should be colored in the same color. And then the map makers have this empirical observations. They realize that they only need 4 colors. Now, it took quite a while. I think for quite a long time, people are able to prove mathematically 5 colors will be enough, but they cannot push it down to 1 more color. The problem finally solved, in quotation mark, not in the usual mathematics way, because 2 guys, I think Kenneth Apple and Wolfram Haken from University of Illinois Urbana-Champaign, they have a device of whatever a map is, reduce it to a number of cases. A number means 1,000 here. So they basically run the computer and check each of the about 1,000 cases. They are all solvable by 4 colors. I remember when I applied to graduate school, now you know my age, in 1979, I went to University of Illinois Urbana-Champaign. At that time, people don't send email, right? I mean, email does not exist. They send me the envelopes, and on the chalk it says 4 colors suffices. They are pretty proud of their result, all right? The computer ran about a month, I was told, in order to verify all the cases. And it is very controversial at that time because people argue that no one has written another program to check that program. I mean, how would you be sure that particular program has no bug in it? Okay, so I think further development is that there are people who reduce it to substantially lesser case, and it's been also and after reducing it to a number of cases, it's brute force kind of verifications. So it's not very elegant, but it does prove it. So if 3 balls are randomly drawn from an urn containing 6 white balls and 5 black balls, what is the probability that one of the drawn balls is white and the other 2 black? All right. So there are the balls. There are 6 and then there are 5. So I have 11 number of balls in the urn, and so I pick 3. So there is this number of ways of doing it. And since I wanted to have 2 black, so the black has to come from the 5 black, and then the remaining white has to come from the 6 white. So it's 6 choose 1, 5 choose 2, 60 ways, and this is 4 out of 11. So I think I would stop here, and then we'll continue on Friday. I don't know whether you are aware of it. Originally, there are 10 tutorial groups, but the enrollment we were expecting was about 400, and now the department has decided to let a number of you appeal for taking this module to be admitted. So I think our enrollment shoots up to something like 500 something. So we have 4 additional tutorial groups being open. So altogether there will be 14. I don't know whether you can see it in your whatever things that you are signing up. Yeah, okay. Okay, so I'll see you on Friday. Oh, yeah.
So I'm going back. Oh, great. Always nice. I'm gonna ask him this question. Yeah, make it follow each other. Oh, yeah.
Yeah, I guess I want to see what he says.
Okay.
If not, the shop.
Oh, you have to take leave.
Actually, you should take leave.